Hello, and welcome to this Paratherm Heat Transfer Fluids webinar. My name is Matthew, and I'll be your Global Spec moderator, and I want to review a few housekeeping items with you before we begin. Please take a moment to familiarize yourself with the operation of the user interface for today's webinar. The large window with the heading Presentation in the upper left is the primary window for today. Just to the right of the main presentation window is the speaker bio window with background information on today's presenter. And just below that is the Q&A window. At any time during the presentation, you can enter a question into the box in the lower section of the window and click Submit. Your question will be placed in the queue to address when we get to the Q&A session. At the bottom of your screen, you will see additional buttons to enhance your webinar experience. To see what a particular button does, just place your mouse pointer over it and a tooltip will appear with a description of the button's function. Now let me introduce today's presenter. With us today is Ryan Ritz, the Global Director of Technology for Paratherm Heat Transfer Fluids. To read more about Ryan, please look at the speaker bio window right next to the main presentation window. And Ryan, welcome to today's event. And with that, I will pass things along to you to get started.
Thank you very much, Matt. And thank you for everybody who is attending with us live and is showing the interest in how to become a more ideal thermal fluid user. So that's really the topic of today's webinar is trying to formulate a best practices guide for what that means to be a more effective, more efficient, more responsible user of thermal fluid systems. So, you know, the target for that isn't just an operator of a system, but instead it aims to reach out to plant managers, engineers, decision makers, procurement folks, anybody really that's a stakeholder in the thermal fluid system in an operation. With that, let's go through our to-do list. And what you'll see, kind of the theme throughout here is, as a thermal fluid user, we're trying to present this in a way that's from the desk or from the knowledge bank of those with expertise on the subject matter, right? So this is in a way, a wish list of what the attributes would be for an ideal thermofluid user based off of the experience of somebody who's been dealing with the aspects and the intricacies of this technology for decades. So we're going to go through an introduction of that concept in a little bit more detail, kind of set the stage for what we're talking about. We're going to be then giving you a little bit more of a narrow idea of what the scope of information is going to be, defining some of the key terms and really giving you the ideas of what this is going to be limited to or what you can expect to gain from it versus what won't be included in the time that we have. And then we'll really spend the majority of the time on item 3, which is reviewing that wish list of attributes that would make up an ideal thermal fluid user based on the perception of an expert in the field. And then with the time we have left, any questions that might arise throughout the presentation can be saved at the end, typed into that chat box, and we'll organize that and answer as many questions as we possibly can. Okay, so starting off, let's get into this introduction. You know, the concept is really this. It's designed to be kind of seen as a wish list of sorts from the perspective of a thermal fluid expert, or actually a collective of experts, really, on what the attributes and practices would constitute an ideal thermal fluid user. So I know that kind of runs the risk of coming off as a bit pretentious, you know, a wish list from an expert to the users. But really that's not the intention. It's just meant to be more of a creative perspective on, you know, an idea or an experience-based best practices guide for everybody that's involved in thermal fluid operations. So think about it this way. Imagine, you know, there's a notebook or a journal, and, you know, this is really modeled off the fact that if I look into some of my desk drawers or in some bags or my record keeping, I've got probably 50 or 60 of these notebooks that are full of notes and findings and research and going into trainings and taking notes, or sales calls or service calls, just all these notes that are full of great information. Imagine, taking a notebook of that or a journal full of information that's collected over decades. Somebody specializing in a very specialized focus area of thermal fluids. It's full of research, troubleshooting notes, training notes, fluid attributes and designs. It's a book that's seen the inside of a lab. It's been on customer sites. This notebook's been packed into briefcases, next to a passport, put into overhead bins, traveled the world. The pages might smell like a faint smell of used oil from the lab or from being on site. Tons of knowledge in here. And imagine now that you had access to that expert's notebook or journal, right? The ability to learn from previous mistakes made by other users in the past. You could benefit from previous breakthroughs or things that we could solve or have solved in the past. So really, this wish list, this thermal fluid expert's wish list of attributes that make up what we would consider to be an ideal thermal fluid user, aims to provide a summary of what you might find in that notebook. Okay, so that's really what this is all about. We're going to look inside the notebook, we're going to use it, and throughout the webinar we're going to make a summary of a list of what, based on the experience, decades and years of dealing with this specialized industry, thousands of phone calls, hundreds of site visits, hours and hours of lab research, troubleshooting and benchmarking. We're going to take a look at that and formulate this list that you can use to say, okay, I'm going to prevent downtime, I'm going to run a safer operation and a more efficient operation. So with that, let's take a look inside the notebook and move on with our agenda. So, introduction out of the way, let's define the scope of what we're talking about. All right, so some basics on thermal fluids. What do we mean by thermal fluids? If you are familiar with thermal fluids, if you aren't familiar with thermal fluids and are here to just learn about that, there's going to be a lot of information to get you to that point of being an ideal user. You'll see one of the points that we make about an ideal user is that they are well educated on the technology, or they take the time to gain a basic understanding of the technology. So here's the first lesson in that, or a review for those that have experience in the past. So what do we mean by thermal fluids? Also names for thermal fluid are heat transfer fluids, or HTFs for short. Some industries or folks refer to them as hot oils, other as thermic or thermal oils. But regardless of what you call them or what they're known as, the basic technology and the advantages of thermal fluids is the fact that they're able to generate high operating temperatures at low system pressures. And so that's really kind of a general definition of the technology, but it shows the main advantage. So with steam-fired systems or with direct heating, you might get a lot of high pressures points, you might have a lot of hot spots or localized overheating. And with thermal fluids, that technology was developed in order to create a more efficient, consistent operating temperature capability across the entire system without generating really high system pressures. High system pressures mean more maintenance. They mean more safety potential for safety issues. So whenever you have high pressures in a plant setting, those become the problems. So our presentation scope, because of the time that we have and because we're really trying to narrow down and focus in, we're going to focus on high temperature systems. We're going to focus on closed loop circulating systems, and we'll talk a little bit more about what we mean by closed loop moving forward. And we're going to focus on hydrocarbon-based heat transfer fluids, so non-aqueous. We're not going to really be talking too much about the principles of water glycol systems or any kind of brine type solutions. We're going to be really focusing on the hydrocarbon-based heat transfer fluids to narrow the scope for the time we have. So by that we mean natural organic-based fluids, or what you might refer to generically as mineral oil-based formulations, and then also synthetic organic-based fluids, synthetic organics, or specifically to around aromatic-based chemistries. Okay. So getting a little bit more into what we mean by closed-loop system and talking about the main components of a thermal fluid system, let's start off by talking about your heat source. Okay, your heat source could be also a cooling source as well if you're talking about cooling, but focusing on the high temp, we're going to be mostly talking about heat source. So that could be a fuel-fired heater. It could be a electrically fired heater, a waste heat recovery type system. Whatever the main heat source that's supplying the energy to the fluid, the heater of the system is going to be the main area of focus. So from there, you have heat transfer fluid possibly running through a coil most often, and that is pumped through a pipe. So that brings us to our second main point, which is going to be the circulating pump. You have to have a circulating system in order to get efficient heat transfer fluid. So in a closed-loop system, a circulating pump, whether a centrifugal pump, some kind of a positive displacement pump is usually what you're going to be running into most, but the fluid has to be moving. Fluid flow is key for efficient heat transfer. Keep that in mind as we talk forward. Fluid flow is going to be very important. So flow rates, setting the temperature settings and the flow rates go hand in hand with the performance of the system. So from there, we're operating around, and these process users that you see here, for this example, we have, just to show it kind of a dynamic system, we've got 3 process users that are here. Now, just keep in mind that could be 1 process user, that could be 10. And think of it for our purposes as a black box. This is just whatever the operating system is trying to heat or cool. So if you're looking at, it could be a wood press or a thermal fluid fryer or a jacketed tank that needs to maintain a certain temperature, a reactor or reboiler, distillation column, whatever the actual calling for heat is in the unit is going to be what we're talking about, the process user. That's what's taking the heat energy out of the fluid itself. And then last main component that we're going to discuss is the expansion tank. So the expansion tank, like we said on the previous slide, heat transfer fluids, thermal fluids are designed to achieve high operating temperatures in the system, but without really increasing the pressure of the system too much. And that expansion tank is the reason that that's able to happen. So it maintains a closed loop in the system, but the expansion tank is open to the atmosphere to allow pressure relief as the fluid volume increases with heat. Okay, so those are the main components that we're going to be focusing on and looking at today in trying to make sure that we can become more ideal thermal fluid users. All right, so that's the scope. We've defined the scope. Now let's really get into it. Let's review this wish list. This is a collective expertise wish list of key items and attributes that I and fellow experts in the field that have dealt with thermal fluids, designing them, researching, working in the field, servicing them, talking to customers, talking to experts, working with equipment manufacturers. This is the wish list that we would create to make, not for the purposes of our jobs being easier or anything like that, but for our users to have a better experience, to prevent downtime, to have a safer operation, to get the longest possible life out of the fluid and the equipment that they can. So this is really kind of a summarized list, and let's get into what we mean by that right now. All right, so start off with our list. Okay. And going off what we're going to be talking about here, let's start off with something I always find to be extremely important, and I prioritize this at the very beginning, and that's making sure that as an ideal thermal fluid user, to have that in you, you have to really appreciate the impact of the thermal fluid and the thermal fluid operating system on your overall operation. You know, that's a really important thing. We're aiming to make sure that you're taking not only an interest but investing in the overall impact that this has. And let's discuss that, really understanding and appreciating what we mean by the impact. So we're going to look at this from a perspective of safety, maintenance, efficiency, and reliability. So the impact considerations that we're going to talk about. This is really important. We're talking about something that's going to be high temperature fluid. It's operating in an environment where it's got an impact on the safety of the people that are at the plant. It's got an impact on the equipment investment that's there. It's got an impact on the efficiency of your overall operation. So if you have a heated operation and you're not running it efficiently, you're not only losing out on your energy costs, but you're also going to be prematurely degrading the fluid, putting unnecessary wear and tear on the equipment, the pumps, the inside of the heater, so that the energy duty that goes into that's going to be higher. And, it really can create a downward spiral. And avoiding ultimately production downtime based off of making sure that those things, unexpected problems can arise. See, the thing about heat transfer fluids, thermal fluids, is that they're designed to be a lower maintenance, safer alternative to other heating applications. So over time, what we've learned is most of the problems that end up happening at a customer site or in any operation are because that system is almost treated as a set it, forget it. There's a lot of miscommunication or no communication based around the fluid because it's so low maintenance over time until a problem arises. And then when a problem does arise, it's a very serious problem that can impact all of these things, safety, equipment, shut the entire system down, so you lose production time. So appreciate that. An ideal system or user will appreciate that and know that it's worth the attention and the investment in the thermal fluid system to be able to avoid those downtimes, to run a more efficient operation and protect the investment and ultimately the people. There's a huge impact on fluid selection, and we're going to spend a little time on that moving forward. If you select the wrong fluid, and this is not a fluid brand or anything like that, this is the fluid type and the fluid quality and the attributes that we'll introduce moving forward. If you select the wrong fluid up front, it's going to be a catalyst for accelerated degradation, which ultimately leads to equipment failures, fouls the surfaces, increases maintenance, decreases efficiency, causes safety problems. So appreciate that the fluid selection really means something. We've heard multiple times over my almost 20 years in this industry, it's just oil, just pick one and put it in there. And that's really not the case, and we'll talk about that moving forward on why that's not the case. The impact on maintenance and operating procedures. If you operate outside of the design specifications, the specs are there, the attributes are there, a lot of money and time and effort has been put into designing these technologies, the equipment and the fluids themselves. So staying within those operating specs is important, so appreciating that as well. If you fail to adhere to those basic maintenance practices, and they are basic and they're minimal compared to a lot of other things that happen in the plant, but if they are ignored or if they're not taken seriously, it can lead to some serious irreversible damages on the fluid and the equipment. And then, of course, the primary concern is safety. When you're running a proper operation with the correct fluid within the specs, these are safe, low-maintenance operations. But the inherent dangers of something that's high temp increases exponentially when these factors are taken for granted. So appreciate it. Don't take it for granted. The fact that you're on this meeting, this webinar now, hopefully is a great indication for me that you do appreciate the impact and it's worth your time to learn more about. So what else does that mean? Let's take a look deeper into it. Prioritize safety if you appreciate the impact. So design and operate with safety factors into the point. Don't spec a fluid that's up to the maximum operating temperature that you're going to be at and leave yourself no room for overshooting temperatures. Make sure that you have the safety equipment and gear, PPE, and the pressure release valves and the check valves and the proper signage and the proper leak protection or collection facilities. Make sure that when someone points out, encourage and empower your people on site to identify potential hazards. Look for leaks, look for smoke, look for centralized overheating areas, and make the corrections on that. Really appreciate the impact because oftentimes these things are ignored as just part of the system. It's better to raise a red flag and it not be something than to not do it, and it ultimately down the road leads to some serious problems. Appreciate the impact means that you take the time to understand the technology. Taking the time to sit here into this webinar right now and paying attention is the first step in that. You really need to make sure that you understand the design features of the equipment And we're not talking about being an expert on the fluid or the equipment itself, but know what the equipment does, know the main aspects, know why or how a system heats up, know what the purpose of each piece of equipment is, know the features of the fluid, what makes one fluid more advantageous to have than another, what goes into making a good fluid versus a fluid that's going to lead to problems down the road. Part of that is understanding how fluids break down. Knowing how fluids break down helps you to be able to prevent them from happening. Lets you be able to take an analysis report and really understand why that fluid was either passed or condemned. If you know how the fluids degrade and what the degradation products are, that'll really be an advantage for you. And make sure all responsible stakeholders, operators, maintenance personnel, plant engineers, make sure they go through the proper training on the fluids and the equipment itself. That's going to be really important. New employees come in, make sure they're trained, make sure that there's brushed up on training over the years. I've had to go on site to do safety training after the fact too many times. Someone gets burnt or there's a fire. There was a pressure relief and it shot hot fluid onto the employees. And then they call in a safety expert or a fluid expert to do training after the fact. Make sure everyone's trained ahead of the time and keep up on that training. Okay. Set a realistic budget. This is huge. Okay. Total life cycle cost analysis. That's an important one for me. We look at the fact that the cost analysis is not just the fluid itself, but the equipment, the downtime, the top-off rates, the testing that's going to have to come into play. Making sure that you have enough budget available and don't just go out there and try to find the cheapest fluid that you can put in, because the financial aspects of that are going down the road are going to lead to some serious problems and some serious costs. So always make sure you consider the bigger picture when you're looking at the thermal fluid system. Plan ahead. This is big. If you notice this little blue ribbon over here, this super user ribbon that I have posted, throughout this webinar, you'll see that ribbon pop up. This is something that comes up often that I wish, as someone who's dealt with this for so many years, these things haven't changed. They've created problems for the user, unanticipated costs, and I'm talking about significant costs. And then when a user does plan ahead and use these tips, the ones with the blue ribbons, that has made a huge difference. So when you see a super user ribbon, know that everything else is important, but these are ones that are just in particular come up over many, many years over and over again, that when they're not followed, it causes big problems, and when they are, the user is happy, the system runs really great. So planning ahead, this is really important. I don't know how many times I can tell you that a user will have a fill or a change out, and they didn't order the right amount of fluid, and all of a sudden it's time to start the plant up. They go to fill the system up, and they don't have enough fluid on hand. Or there was a leak, and they don't have enough fluid on hand. So they have to call at midnight or 1 o'clock in the morning, get a rush shipment of fluid. Warehouses need to open, trucks need to get on the road, and the emergency shipping costs and everything associated with that is just not efficient for a good process. So when you have scheduled maintenance activities, you appreciate the impact that can have, you're having a shutdown, try to make sure that you plan ahead and have some extra inventory of fluid around. You're going to be doing a fill, maybe over order, and then work out with your supplier if you can replace the fluid or if you can keep it on site for extra inventory. Consideration of all heated applications. If you have multiple applications with heat transfer fluids, thermal fluids, whatever you might call them on your site, you probably save a lot of money by single source using that. It might not be the same fluid in each unit, but if you have thermal fluids that are used in multiple units, might be different products or different temperature ranges, odds are that you can likely source from a single source, and that will end up probably saving you a lot of money. Not only save you money, but having that inventory of the products nearby or close for multiple units is important as well. And then ultimately, if you appreciate the impact and you truly are invested in this, you'll work with reputable partners, engineering and design firms that have dealt with thermal fluids in the past, equipment suppliers that are well known and can customize or supply you with something in their line that's going to be ideal for your needs. Thermal fluid suppliers have been through this before and experts on this and provide all the services that go along with that. And then testing and service providers after the fact. All right, so we all appreciate the impact now. Next item or characteristic of an ideal thermal fluid user is they take care in selecting the proper fluid. You appreciate the impact and you understand that you need to select the proper fluid. Now let's talk about how you do that. Okay, so proper fluid selection is critical. Heat transfer fluids play an integral role in most industrial processes. Make sure you emphasize the importance of the very first step of your thermal fluid journey, and that's select the correct fluid. That's going to maximize the overall value of your performance, your efficiency, your equipment longevity, your energy efficiency. So many things are decided just by that one simple choice of selecting the proper fluid. You want to make sure the fluid you choose meets your operating specifications with a safety window. You don't want to have something that's going to be operating at the upper recommended point. Yes, it is marketed and designed to operate at that, but understand that there's a safety feature that you need to build in, a safety cushion that you need to build in for overshooting, for operator error, for anything else that might come into it. So take a look at your operating specifications, find a fluid that optimizes those specifications. For your equipment design, certain fluids are better in certain types of equipment, electrically heated or fire heated or coil heated or whatever it might be. You want to make sure you choose the right fluid to optimize your budget. Understandably, there are some fluids out there that are very high performing that might be out of your budget. That doesn't mean that you need to go to the lowest possible denominator to fulfill that need. So again, we appreciated the impact. We set a realistic budget. We got a fluid that was well designed for that. And there are options within all cost ranges that are going to be an optimized fluid for that cost range. Okay. Superior fluids, and this is what we're going to get into moving forward in the next couple slides, will feature these three items, these three key aspects of a superior fluid. A fluid that's got high purification, a fluid that features high heat transfer efficiency, and a fluid that has high thermal stability. And we'll talk about what each one of those means. So real quick, we talked about this in defining the scope, hydrocarbon-based heat transfer fluids, natural versus synthetic. The first choice you're really going to have is what chemistry of your fluid you're going to be using. And there's two main options within the scope of this presentation that we're going to be talking about that you're going to choose between. So you have natural organic hydrocarbons. It's a base chemistry that's really generated from a crude oil refining process. At the origins, it was from crude oil, and it's been refined down. The generic term for the base of these chemistries is mineral oil. They're usually non-toxic. They're very efficient, cost-effective performance, but the maximum operating temperature is really limited to usually somewhere between 500 and 600 degrees Fahrenheit. So if you're operating at or above those limits, you're going to probably want to consider something a little bit more robust in a synthetic product. Really key point about natural organics, quality and purification are critical. Color is really important. So when selecting a fluid, sometimes it's as simple as looking at something that is just the color or the physical appearance can be a really good initial indicator if you're using or respecting the right product or on the right track. So highly refined, specialized, engineered products are well worth the added cost because they're still probably within your budget, and the dividends that they're going to pay down the road are going to be really high. They're going to have higher stability and better performance. On the other side, synthetic organics, base chemistry is specifically formulated from a chemical synthesis. These are most commonly referred to as the chemistry as an aromatic base. They have very high thermal stability. They can offer you temperatures above 650 degrees max operating temperature. But there are some limitations with these products because they're typically derived way down the road from some kind of a benzene-based chemistry. That gives them their ring structure, molecular structure, and the double bonding that gives you better stability. But the trade-off is they're going to come at much higher costs, and sometimes there's some environmental impacts, some shipping impacts. Nothing that's completely restrictive most of the time, but it's something that you need to consider when speccing a fluid. Is if you need the upper operating temperatures that a synthetic product will give you, it's going to come with some trade-off factors in the limitations on shipping, maybe storage, environmental limitations. Just evaluate all that, and the cost is usually going to be higher. All right, some of the fundamentals. Maximum operating temperature and minimum operating temperature. Obviously, that's going to be really important. You're going to purchase a fluid that's capable of reaching the maximum operating temperature. Also consider the climate and the environment that you're in, because that's going to determine your minimum startup temperature. If you're in an area that you need 550-degree operation, but when you fill that system and you go to start it up, or if you do maintenance and you go to restart the system, and you're in a cold weather environment that you're in the negative temperatures or you're in really low temps when you go to start up, you need to make sure that you have a fluid that's able to perform under those low temp startup conditions. So check those boxes. Make sure that the fluid not only meets your maximum operating temperature, and keep that in mind, operating temperature, not the maximum of the heater itself, but what the actual process user needs, what the outlet temperature of the fluid is going to be. Make sure you leave yourself a cushion there. The closer you are to that maximum operating temperature that the fluid supplier recommends, usually the less life the fluid's going to have long term. Okay, so make sure that you can have that cushion. Make sure that the fluid also can be pumped and efficiently heated at whatever the minimum startup temperature you're going to be. That's all going to be listed in the product literature if you're dealing with a legitimate product. Process considerations. Make sure that the fluid's compatible with whatever, if you have an existing fluid system or an existing system that you might have drained out and are refilling, you want to make sure that you're not putting in an incompatible product with what was there before, or your materials of construction are going to be compatible. Okay, you never want to put a water into an oil-based system, for instance. But also, you might not want to mix synthetics with mineral oil-based products. You really need to take that into account and talk to your fluid supplier before you make that decision. Enhanced equipment controls, that's an important process consideration. If you're operating, we'll talk about that moving forward. We look at oxidation in the expansion tank, what we mean by inert gas blanket. That can also mean filtration systems. These are all ideal system advancements that we will talk about moving forward. Local climate extremes for the minimum startup temperature, and then obviously budgetary factors, cost versus performance optimization. Yeah, it might be great for you to have a synthetic product rated up to 675 degrees, but if you're operating only at a temperature of 400 degrees Fahrenheit, it's probably going to be overkill for your budget. So you want to make sure that your costs associated with performance optimization is really taken care of. And then the total life cycle analysis, to me, this is extremely important. And this is another super user point. The cost of the fluid itself is nothing in comparison to the capital cost of the equipment, which pales in comparison to the production assurances. If you have downtime, well, how much money does that cost your plant? And then ultimately, if you have a safety issue or something really goes wrong and there's loss of life or injury, the costs of that are incalculable. So you need to make sure that you take the total life cost cycle into analysis. It's not just about the fluid. It's about when that fluid, an inferior fluid, breaks down, it affects the equipment. When it affects the equipment, you're talking about plugging lines and fouling surfaces. When that happens, that creates more maintenance, that causes more wear and tear on the pumps and the heater and the pipes and the integrity of the metal and the valves, and can eat away at seals, and there's all kinds of issues that can create. So total life cycle analysis, top-off rates that you're going to have to do, testing you're going to have to do, change-outs. If you're going to have to dispose of the fluid, that's going to be a cost down the road. So take that total life cycle cost analysis into play when you're specifying a fluid itself. So engineered fluids, and this is important. I like this term, engineered fluids. Over the course of doing this for a long time, I've seen a lot of different fluid formulations that feature a lot of unnecessary design aspects. A lot of stuff that might be great for a lubricating system or for a turbine system or any other kind of multi-purpose industrial oil. But when you put those features or you formulate around those kind of additives into a thermal system, you don't get the advantages that you think you're getting. It's actually detriments. A lot of those additives, a lot of those technologies and chemistries that you put into fluids like that will actually take away from these three key features that we're talking about. An engineered fluid takes the fluid chemistry itself, takes a formulation, and balances these primary factors: thermal stability, heat transfer efficiency, product purity. Some secondary considerations we put into play when we're trying to design a good fluid and that you should be looking for, but never to trump the top three. The secondary considerations are expansion rate. You know, make sure you size your equipment properly. Obviously, your startup temperature is going to be important. Vapor pressure, and then cost versus performance. Lower priority factors, oxidation resistance. Now, that might seem a little counterintuitive, but this comes down to the fact that a lot of times over-additizing a product to resist oxidation ends up causing a lot of problems for thermal stability. Thermal stability, we'll talk about that on the next slide, comes down to the point that you really need to make sure your product can handle the heat that it's going to be exposed to before all else. There are equipment modifications you can make and procedure modifications you can make to help with oxidation resistance that won't end up hurting your thermal performance. So you can't control thermal performance as well as you can control oxidation with the equipment. So that's something to take into consideration. An oxidation-resistant fluid that's formulated for that will end up hurting your thermal stability down the road. And then flash and fire points. For you safety managers that might be on or listening, please understand that we don't think that fire safety is important. We do. Obviously, that's prioritizing safety as a key impact. But a super user will understand what flash point really means. Flash point, I'd say the greater majority of thermal fluid system operations are operating well in excess of the fluid flash point. And when you really take a look at what flash point means, how it's tested for in the lab, it's more commonly used as a shipping and storage feature or data point than it is an operating data point. So understanding that you can operate above the flash point, it is very common and it's done safely because the aspects that create that number, that data point, don't really exist inside of a closed loop circulating system. So our three key primary performance factors: high purity. The level of purification goes beyond just a toxicity consideration. Impurities in a fluid catalyze degradation. So those impurities will actually foul out, coat the surfaces, create solids in your system before the fluid molecules actually break down. So when you foul those equipment surfaces and you continuously expose those fouled surfaces to high operating temperatures, it's just going to accumulate on the surface and create more and more problems down the road. So high purity is very important. You want to make sure that the fluid that you're using is able to stand up to the temperatures that you have, and the additives or impurities left from the crude oil refining process, or if something is formulated with way too many additives, those impurities are going to foul out onto the surfaces and cause problems. So you want to make sure you're specifying a high purity product. Pay attention to the SDS. Look at the colors. Usually with especially a mineral oil-based product, the purity level can really kind of be indicated by color. A lot of color, a deep yellow or an amber, an orange, straw colors, anything that's really tinted with color is going to show one or two things. Either way too much additive has been put into that formulation that's unnecessary and going to cause problems, or the fluid itself was not taken to purification levels and distilled out in its production phases. So there's a lot of impurities left from the crude oil refining. You want to make sure that you just look at that, simple enough. If you're comparing three products and one is clear, that's a pretty good early indicator that the purification levels are going to be good for that product itself. High efficiency. This is calculated using thermal properties of the fluid and the operating conditions. So you can take your flow rate, your temperature set points, and your pipe sizes for any system, and then plug in the data values for the fluid. This is the most important being the viscosity, the density, the conductivity, and the heat capacity. Now, we're not asking you as super users to be able to do these calculations. That's on the fluid expert, right? But understanding that they're there, they're capable of being calculated, and they make a difference is important. So a more efficient heat transfer fluid or thermal fluid will feature a great mix of low viscosity, high density, high thermal conductivity, and high specific heat capacity. Now, as an ideal fluid user, what we're going to recommend to you is this. If a fluid that you're specifying or looking or considering does not have those four data points available across, it's very expensive and very time-consuming to get the viscosity, the density, the conductivity, and the capacity across the entire range. In order for a fluid formulator or a fluid designer to actually design and create a new fluid, they would have to make sure that they tested around all of those factors to give you a more efficient fluid. So if the fluid supplier doesn't have that data available to you across the entire temperature range that you might be considering, the odds are that that fluid wasn't intended to be a heat transfer fluid to begin with, or a thermal fluid. So that's a good indicator. Make sure, insist on that data, see if they have it, use that as an indicator or qualifier if it's a reputable supplier or not. And then thermal stability, the fluent's inherent resistance to damages from the heat. So this is done with a lab test. ASTM D6743 is the test. Really what it comes down to is a simulation in a lab oven of what's occurring inside of your heater. So you can test all the tests before, all the key properties of the fluid, put a stress test on two fluids that you're trying to compare to each other inside this oven. This happens over the course of 500 hours for that ASTM test. And then you measure all the same properties and how much degradation material and how much the fluid broke down afterwards. And it gives you a great indication, and we've verified a lot of this and justified this test with our experience in the field for doing this for 35 years. And the higher thermal stability will give you a longer lasting fluid, but even more importantly than the longer lasting fluid, it gives you less maintenance over time, less wear and tear on your equipment, and an overall total life cycle analysis that's going to be better. So we talked about taking care and selecting the proper fluid. Next, we are going to get into following proper startup procedures. Okay? So you've selected the proper fluid. You've worked with a reputable supplier on your equipment. Your design is in place. The safety features are there. A lot of times, even if all of that has been taken into account, just by improper startup of the system, the user makes irreversible damages and causes problems right from the beginning. So what do we mean by proper startup? First and foremost, proper startup of a system, you want to make sure, and it's not mentioned on this slide, and I apologize, but you want to make sure you have a clean system to start with. So whether you drained a system and refilled, or you maybe had a brand new system commissioned, and for some reason someone decided to use a cleaning agent beforehand, you want to make sure there's no moisture in that system. There was nothing water-based introduced into it. So that's really important. Starting up with a clean system is really important. But once the system is filled properly, following the procedures from the equipment manufacturer and the fluid manufacturer, you want to make sure you start up properly. When fluids are colder, they have higher viscosity, which means that they're going to stick to the walls of the pipe more. It means they're going to have problems and stick to the heated surfaces and break down faster on the pipe walls. So a low temperature, more viscous fluid, not thermally efficient. If you put a lot of temperature, a lot of heat energy onto that cold fluid right away, you're going to shock the fluid basically and crack the fluid onto the heated surfaces. So you want to make sure that you start up slowly when you're initially starting. Don't let that heater go into high fire until the fluid reaches what we call turbulent flow. Turbulent flow means the flow rate is good enough to remove the fluid and get it moving. So turbulent flow happens usually around 180 degrees Fahrenheit. You want to talk to your equipment manufacturer for that. When you're shutting down the pipe, the system, you don't want to ever shut the pump and the heater off at the same time, because then you just have fluid sitting inside of a hot heater box baking into the heater. So you want to make sure you keep the main circulating pump running after the heater is powered off. All right, so that's proper startup procedures. Next, we're going to talk about adhering to design operating conditions. Okay, making sure you can recognize red flags and take action. So, routine system, know your system, all right? Listen and look. Know what it's supposed to, the gauges are supposed to say. Know what the set points are and the operating conditions. And if something is going away from that, that's a problem. These are designed to maintain and stay within a certain range of temperatures, a certain range of pressures, a certain flow rate. So if you're hearing sounds or you're seeing gauge readings that are off, that's something you should act on. At least raise the issue up higher and then talk to an equipment manufacturer or talk to your fluid supplier. Take a look at your differential pressures. That's going to show you the flow rate between your heater inlet and outlet. So if that pressure changes, then there's something inhibiting the flow through the heater. That can cause cracked heater tubes, which can ultimately cause problems down the road. In the case of maybe a fire or a leak or potential high maintenance activities. The exhaust stack temperature, that's an important one to read too, because the heat that's not going into your fluid is going out of the exhaust stack. So take note of what that is under normal new operating conditions. If that exhaust stack temperature starts to rise over time, that's energy that used to go in the fluid and is no longer doing that. It's going out into the atmosphere. So there's a problem. That's a red flag. So record your readings, monitor report changes, know the signs of degradation, and get your fluid analyzed. So heat transfer is just energy movement. You need proper flow for that to happen. So the way a typical operation works is you have your heat source, That heat source is going to transfer energy through the wall of a pipe, through the wall of the pipe into the thermal fluid. The thermal fluid then needs to carry that heat energy out to whatever your heated process is. So looking at that a little deeper, degradation factors that can happen along the way when you're not doing that efficiently, when that design of the fluid isn't working properly, these are the things that can happen. Thermal cracking or overheating the fluid. When you have too much heat energy applied at that pipe wall, you're going to be cracking the fluid. It breaks the molecular bonds, generates low boilers, carbon solids, and reduces heat transfer. You always want to make sure you operate inside your design specs and don't deal with, or make sure you're properly starting the system up and shutting it down. Oxidation is when a hot fluid is exposed to air, increases fluid viscosity, sludge formation, elevated temperatures in the expansion tank are usually the cause. Let's take a closer look at in your operation to search for this red flag. Look at your hot spots, all right, inside your heated source. Let's take a look at inside that coil. You've got thermal fluid flowing through that coil, but you have high heat flux at your pipe wall. That heated surface, if you don't have proper flow or you've got other issues going on, you have an inferior fluid, the heat is not going to go out into the system. Instead, the energy is going to be used to break the molecular bonds. When the molecular bonds of the fluid break, they create carbon fouling or carbon solids onto the walls of the heater. That creates an insulation layer that blocks the heat from getting to the bulk of the fluid. If you have that heat being blocked to the bulk of the fluid, it's going to then build up more and more and more. Usually what ends up happening is a non-ideal fluid user will then say, okay, I'm not getting the heat I need. My fluid's coming out colder than it should. I'm going to increase the temperature by 10, 15 degrees. When you do that, you end up just compounding the problem, putting more heat energy into the fluid, breaking it down even faster, maybe even doubling or tripling the rate of degradation, and that just causes the compounded problem to go over and over again. So raise the red flag. Looking at your expansion tank for red flags. Let's look at oxidation. How does this happen? You've got fresh oxygen coming into the expansion tank through the vent to the atmosphere. When you have oxygen mixing with hot fluid, okay, thermal fluid plus heat plus oxygen equals oxidation. The product of oxidation ultimately is high acid number, which then mixes with the solid particles from the degradation and creates something we call sludge. So the products of degradation, low boilers, high boilers, these are just changes from the intended design of the fluid. Sludge buildup, solid carbon, and as these items build up, the efficiencies go down, the flow rates go down, and the degradation just starts compounding, and you get into a negative swirl where ultimately you're going to have plugged lines, you're going to have flow issues that you might not even be able to get the system started, and you can lead to a lot of maintenance and a lot of downtime if this happens. So recognize those red flags and take action on them. Okay. The next ideal thermal fluid user aspect is implement a consistent PM program and regular housekeeping. The fluid degradation over time is going to happen. No matter what fluid you're using, no matter how great your system is, you are going to get some fluid degradation over time. It's just the nature of what goes on. But because it's inevitable, it doesn't mean that we can't control it to an extent. So our goal is to minimize the rate at which it happens. So ensure that your fluid is actually designed. We talked about that safety cushion. You don't want to specify a fluid that is spec'd right up to what your operating temperature is going to be. Leave a degree of safety there. Leave a degree for error. Because if you increase the fluid 18 degrees over its max bulk temperature, you'll cut the life of the fluid in half. So you want to make sure the closer and closer you get to that higher operating temperature, you're cutting the life of the fluid in half, then in half, then in half over and over again. Always want to make sure you maintain the design flow rate and always follow those startup and shutdown procedures. To prevent oxidation, keep the expansion tank below 150. Never insulate the outside of the expansion tank. Remember, we said you need heat plus fluid plus oxygen for oxidation to happen. If you can't control the heat, then you got to control the oxygen level, and you can do that by putting in an inert gas blanket. That's another super user tip. If you can't keep the fluid in the tank below 150 degrees, installing an inert gas blanket to displace the oxygen inside that tank, but without really affecting the pressure and still giving that safety feature is going to be important. So, the consistent PM program and regular housekeeping practices. Another thing that goes along with housekeeping, obviously, keep things labeled. Keep your drums or containers of fluid stored in an area where they're not going to take on moisture. Keep the labels on those drums clean and clear. You wouldn't believe how many times we've had to have analysis done on a brand new drum because somebody lost the label and we had to tell them if it was our fluid or not. So that's a really important one as well. To me, this next aspect is extremely important, and that's fluid analysis. You should be getting a fluid analysis done minimum annually. A fluid analysis is the most reliable tool for keeping your system running at an optimum level and avoiding unexpected problems. You should be getting this as a preventative maintenance practice annually, but also after any major changes. If you're going to be changing fluids out, adding fluid, if you have any questions or any of these red flags in your head that we talked about previously, as an ideal user, you're always looking for red flags. You've recorded your readings, your exhaust tach temperatures. If any of that changes to the point where it's a concern, call your thermal fluid supplier, and maybe just getting a fluid analysis will either help alleviate some of that stress or justify the fact that your red flag was actually there, right? So you can tell a lot from a fluid analysis. That being said, make sure that your fluid analysis that you're getting on your thermal fluid is specific to thermal fluid or heat transfer fluid. Very often we see people getting fluid analysis done on a lube oil provider because it's easier to send all your fluids out to the same lab. Though they may be similar tests and similar ASTM methods, the condemning values for a thermal fluid and for any other kind of industrial oil could be very different. So you want to make sure that you're dealing with somebody who's testing based on those values specific to thermal fluid system and not just any other industrial oil. Most of the time you can have that done either through or by your fluid supplier. So if you specified and used a reputable supplier, they're going to be able to set you up with good testing capabilities. Another really important thing, you want to make sure you have a full report of your condition. That includes expert recommendations, not just the values and if it's condemned or not. There's a lot of gray area when you're condemning a thermal fluid. It depends on the temperatures that you're running, the cycles you're running, how long the fluid's been in there, what it looked like 3 years ago versus what it looked like last year to this year. A lot of stuff can happen in that time period. So you want a verbal review on your results, maybe we'll talk to the experts, and then consider the best practices for either controlling the degradation or removing the fluid. You need a plan of action, and you need to be able to work with a reputable supplier for that. So that's a super user tip. And I know it's a basic one, but it's one that I'd say I wish 100% of all users did a strict fluid analysis program, but unfortunately it's probably more like 25%. And it's something so easy and something so useful that if you really appreciate the impact of your thermal fluid system, having a regular fluid analysis program is going to be important. So what are we testing for? We're testing for the acid number to show the level of oxidation. These are just some of the condemning values that we find. We test for the viscosity to make sure that the fluid hasn't become too viscous or too thin. The viscosity might go down as well for efficient heat transfer. Remember when that formula for testing efficiency or calculating efficiency, viscosity was a really important value. It helps determine the flow rate. It helps determine the amount of time the fluid is exposed to the walls of the pipes. So a change in viscosity will change the efficiency and is a real indicator of some other red flags in the system. Measuring the distillation range of the fluid, the composition for altering and overheating. So we run this through a simulated distillation sometimes, or it could be a vacuum distillation. Most of the time it's going to be simulated. It shows you the molecular structure, how much it's changed. If fluid's been overheated, or if there's a sludge buildup, something like that, or even if there's a contamination, the distillation range should really help to narrow that down. So an increase in high boilers, an increase in low boilers are red flags. A change in the distillation range on the high or low end will reduce the heat capacity of the fluid. Again, flashpoint. I know we said we need to understand flashpoint, and this isn't so much for the safety aspect of the flashpoint itself, but if there's a substantial change in the flashpoint, that means that there was a substantial degradation factor that happened to that fluid. In order to significantly change flashpoint, the molecular structure of the fluid probably changed a lot. So that's just another red flag that we would look at for the flashpoint. And then we can do other tests, like if we consider there might be water in the system, if there's a lot of solid buildups, we can do tests that focus around that. All right, so next aspect, fluid analysis, checked off. Very important. That's why it's capitalized with explanation points. Finally, an ideal fluid user will maintain active relationships with all key stakeholders. They'll keep all of their staff well informed and trained. Communicate on-site. Okay? Stakeholders aren't just outside, they're internal as well. Schedule regular equipment inspections with your equipment manufacturers. Have them review what's going on. Follow their PM programs. Uphold that strict fluid analysis program, annual at a minimum. and insist on an in-depth review of the results and recommendations. Maintain good records. This is another super user area. Volumes. If you know what your volume is when you first build the system. So many times you go to refill a system or top off or add a certain percentage, and the user has no idea what the original volume in the system was. Or equipment's been added on. They have no idea how much that changed the overall fill volume. So keep records of your volumes, whatever you added, whatever the initial fill was. Keep records of your maintenance activities and your fluid analysis reports. This goes a long way for helping us to troubleshoot when problems do arise. And always consult with your equipment and fluid experts on any changes, concerns, or red flags you see. Never compromise on that service support. All right, so with that, we are coming close to the end of our hour, and I know we rushed through a lot of that at the end, but we did get through what the entire list of our ideal thermal fluid user is, based on the experiences that we've had out in the field for all these years, knowing what makes a good fluid versus a bad fluid. There's a lot of great fluids out there, but there's even more bad fluids. There's a lot of great operations out there, but there's even more things that are ignored. So ideally, everyone would become an ideal thermal fluid user, and these are kind of the tips to get you started. So with that, reviewing our wish list is over. Let's move into Q&A with the time we have left. I think we have time to get to a few questions. So Matt, I'll pass it over to you to get into that.
Yes, indeed. And thank you so much for that great presentation. That was awesome. Thank you very much. And yes, to the audience, we are moving into the Q&A session. We have a few minutes for some questions. If we do have quite a few questions in the queue already, so thank you very much. If you haven't submitted your question yet, you can still add that in the Q&A box and click submit. We'd love to hear if you had a question or even a comment. Please send us your thoughts. Like mentioned, we only have a few minutes left, but we're going to try to get to as many questions as we can. If we don't get to your question, we will have an answer for you following the webinar. So please send them in. Okay, now let's see our first question from the audience, and here it is. Why does thermal fluid darken quickly when compared to its initial color, which is transparent? Ryan?
Yeah, so that's a great question. There's a couple of reasons why that might happen. One, there's no system's going to be completely clean, right? So the inside of, even if it's a brand new system, the inside of the pipes are going to have some varnishing. They're going to have, some kind of leftover from the oils that were used to generate the pipe. A lot of times the thermal fluid will pick that up when it's brand new, but I think the question is more relevant to use thermal fluid over time. Now, if it's a system that had fluid previously in it, even if you drain the system out fully, probably about 15% of that old fluid is going to be left in it, right? So that's going to be something that's going to change the color of the fluid. But most commonly, due to wear and tear, thermal fluids exposed to heat, the degradation product is actually, they're hydrocarbons. So when they break down to carbon. Carbon soot is black. So believe it or not, it's due to the thermal fluid breaking down due to the heat stress, creating really, really microscopic carbon soot molecules that suspend throughout the fluid, and that really just changes the coloration. Now, that being said, that's natural. Like I said on that one slide, degradation is going to happen over time. Color is usually a good initial indicator, but like you said, most thermal fluids over the initial year or two will turn darker. They'll get darker brown or even somewhat looking like they might be black. It's a good initial indicator, but it's never going to be a condemning factor that the fluid turned dark. That soot buildup is just changing the color. When it starts to break out of solution, when you look in a sample jar and it starts to settle to the bottom, when it starts to pluck up lines, that's where it becomes a serious problem. So the color is not necessarily an indication of degrading or condemning the fluid, but it might be a good indication if you see the color change rapidly or something you don't expect. Send that in for a fluid analysis. Let's really look at it to see if the properties themselves change or it's just due to that carbon soot. Good question.
Very interesting. Thank you for that. Yeah, and thank you for the question from the audience member. That was great. We have more questions coming in, so to the audience, please keep them coming. Like mentioned, if we don't get to your question, we will have an answer for you following the webinar. Okay, now here is our next question from the audience. Could you mention a few industries where thermal fluid is predominantly used?
Sure, really, there's so many that are out there, but some common ones, food processing for thermal fluid fryers, the chemical industry, reboilers, distillation units, reactors, the asphalt industry, road asphalt, for manufacturing the hot mix or keeping the tanks hot for the fluid to be able to be transferred properly. There's the wood industry that creates wood paneling. So you've got a heat press. You have to heat the glue or whatever the adhesive is and the wood particles to make a wood panel and press them together so that panel would be heated. Think about any process that really needs to have heat control in order to be manufactured, and you'll probably find a heat transfer fluid or thermal fluid somewhere in the line to make that happen.
Oh, very cool stuff. Thank you for that. Okay, and to the audience, now is your last opportunity to send in any questions or comments. Looks like we have one more question in the queue right now, but if you do send something more in, we will reach out after the webinar is over to provide an answer. And we thank everybody for all the questions and comments so far. This has been great. Okay, and here is our next and most likely final question, and here it is. Can you elaborate more on how having operating temperatures above the flash point is safe?
Okay, great question, and it's a question that we get constantly, probably weekly. So thank you for asking. Okay, so really, when you think about safety, ultimately, we're considering the fact that it's a system that's designed and following under its design specs to be safe, first and foremost, right? So you've got a system that is properly designed. You've chosen a fluid that is going to be ideal under the circumstances that we talked about previously. Under those circumstances, in a closed-loop heat transfer fluid system, remember, what does it take to have flash point? It's done in a lab, okay, and the flash point takes three things. It takes fresh oxygen stream constantly at the surface of the fluid. The fluid itself is not what flashes, but the vapor on top at the surface of the fluid is what flashes under that test. So you've got fresh oxygen stream, you've got an accumulation of concentrated vapors not ventilated at the top of the surface of the fluid, and then you have to have the third thing, which is an ignition source, a flame or a spark, electrical arc, something like that. Okay, so under those three things, in a closed-loop, properly designed system, you never actually have the combination of those three things to generate a flash. You do not have an ignition source inside of the pipes, even though your fluid might be at the temperatures that are higher. If you do have vaporization of the fluid, it's going to be at some kind of a weak point in the system where it might be a fitting or a valve, and at that point, that fluid's going to be ventilated out into the atmosphere or oxidized into smoke and no longer vaporized, concentrated to where the flash point matters. So you might have a 500-degree operating temperature, but a 350-degree flash point, but those three items, in order to create that flash point, are never put together inside the system itself. The only time flash point really comes into consideration if you have a catastrophic failure of the fluid where you have a leak into the heater box, and then you have an enclosed space with no ventilation and obviously extremely high temperature. Under that circumstance, the flash point of the fluid no longer matters. In those conditions inside that heater box are going to be well above whatever any flash point of any fluid is. So under normal operating conditions in a well-designed system, your flash point never comes into consideration because you don't have that combination. There's three necessary items: ignition source, oxygen, concentrated vapors of a heated fluid. Okay.
Thank you for that. And it looks like that was our last question for today, so we are going to wrap things up right there. So Ryan, thank you so much for taking the time to be with us today and also taking the time to answer some questions from the audience. And of course, we'd like to thank our audience members for being part of this webinar event. You will be receiving an email from us with a link to the on-demand version of this presentation, so you will be able to come back and watch this again or share it with your colleagues. And lastly, please take a moment to complete a survey, which will appear on your screen at the end of this live webinar. For on-demand viewers, you will find the survey located along the bottom of your attendee console in the survey widget. Again, thank you for taking the time to attend this webinar event. Take care, and we'll talk with you soon.